So good morning. Thank you for being here today. We are HeatFlex, and we're going to be discussing our flexible heating composite that we developed as part of our FYDP. I'm Amanda, that's Mayuran, and that's Tuba, and we're going to be your presenters for the day. So people often find themselves unable to generate sufficient heat without external aid. Now, in such cases, purely insulating materials are not sufficient. While there's great benefit to heat generation, current heat generating technology is both bulky and rigid, two very undesirable characteristics when it comes to wearable materials. Now, this is the impetus to develop a self-regulating, self-heat generating, flexible material for applications in apparel. As mentioned earlier, current heat generating technology is both bulky and rigid, two very undesirable characteristics. Technologies that incorporate rigid heating elements are prone to damage, and exposure of these elements can also be quite hazardous. The alternative to this would be using heat packs. However, heat packs also pose a risk in terms of burns, given its exothermic reaction required to produce the desired heat. Short-lived and uncontrolled alternatives provide the impetus to explore technology which both supply and regulate its delivery. So skin plays a very important role in human thermoregulation. As shown in this graph, when your hand and your foot are very cold, you feel the most uncomfortable. As a result, our composite targets applications relevant to heating the foot and the hand, such as incorporation in a shoe sole or in a glove. So I'm going to talk a little about the customer requirements, focusing mainly on the primary requirement. The first requirement, as shown there, is to develop a self-heating, self-regulating material. The second would be to ensure that a steady temperature is held at 37 degrees centigrade with convergence on 37 degrees Celsius within 10 minutes of fluctuation in the external environment. In addition, biocompatibility and non-toxicity is also very important for our device, given that it's in very close contact with skin. We're going to move on to engineering design. Now, heat is generated in our material through Joule heating. Joule heating is the dissipation of electrical energy in a conductor through the generation and transmission of heat. When a voltage is passed through a conductive element, particles are brought into motion and they collide randomly, generating heat, which is then released into the external environment, which is how heat is generated for our material. In order to meet our customer requirements, and in order to bring about Joule heating, we use graphite in a PDMS matrix. PDMS imparts it with flexibility and durability as well. So heat generated by Joule heating is regulated by that equation shown up above. In order to raise the temperature by 1 Celsius, the following relation must be met. And current modulation is how we regulate temperature in our device. So when it comes to wearable material, the material needs to be flexible, durable, and compatible with human body movements. It should be able to mimic the movements of the human body and potentially endure stretching, twisting, and various other contortions. As such, PDMS was chosen as the matrix material, given its strong and versatile mechanical properties, such as high flexibility, ease of molding, biocompatibility, chemical inertness, and hydrophobicity. The second mechanical requirement is mechanical integrity and durability, which again is brought about by our PDMS and our composite. So at various stages, we faced some design decisions. The very first one was choosing a conductive carbon filler. We explored graphite powder, carbon black, and silver nanowires before finally settling on graphite powder as our conductive element. The second decision that we were faced with was choosing an electrode material. Copper tape and nickel foam were explored. We finally settled on copper tape given its ease of availability and relative inexpensiveness as compared to nickel foam. And finally, I'm going to talk a little about the design trade-offs. So one of the trade-offs that we faced was flexibility versus conductivity. Flexibility, as mentioned earlier, is brought about in our composite by PDMS, while conductivity is brought about by the conductive element, which was our graphite powder. However, increasing conductivity by loading of the material results in a decrease in flexibility. We finally optimized these parameters and settled on a loading of 40% to ensure that both flexibility and adequate conductivity were met by our material.
So as Amanda mentioned, one of our targets is not only heat generation, but heat regulation as well. And therefore, we had to bring some smarter elements into our system. So we have here an Arduino Micro, which is the sort of brains of the operation, and also temperature sensors in the form of thermistors. So thermistors are basically resistors whose resistance will vary significantly with temperature. And so we have these thermistors embedded within the material to gain an accurate representation of what the distribution of temperature is inside the material. And this allows us to create sort of a feedback system where we're not only monitoring, but regulating the temperature as well. So what we do is we measure the temperature within the material and then decide with the microcontroller how much current to supply to maintain a set temperature. So for example, if a customer believes that 29 degrees Celsius is what they deem comfortable, we can ramp up until we hit that set temperature and just maintain it for the remainder of their usage. So here's just an example of one of our test setups. So on the right here, you see an infrared imager. So basically, it's measuring the infrared radiation put off by our material. And we decided to use this to gain an accurate understanding of what the heat distribution was, to explore things like uniformity and heat mapping. So some analysis. Obviously, one of the first characteristics we had to look at was IV curves, just this current to voltage relationship and how it varied, and then therefore how we could determine, consistency in how we were fabricating our material. And obviously, our huge concern was heating and cooling profiles. So what we have here is a heating profile where we're supplying about 1.5 amps of current through our material. And we're just exploring how long it takes to achieve, certain set temperatures. So we can see that within 4 minutes, we already hit the desired 37 degrees Celsius that we had in our customer requirements, which is pretty impressive. And as we continue, we can hit the upwards of 50 degrees, which is well beyond what we require for applications in apparel. Next, we really wanted to explore uniformity inside the material. So we have about 5 thermistors embedded in our polymer. And so what we wanted to see was to make sure that we were getting uniform results throughout. So here we have 2 thermistors at the top and bottom. And we see pretty symmetric results where they're reading fairly similar temperatures. But the real problem arises when we investigate different ends of the material, where we're placing thermistors at opposite electrodes. And because how the voltage is dropping, we're going to notice significant variations in temperature initially. As time progresses, they will equilibrate to somewhat of a similar temperature, but it's still an issue in the beginning. So what we decided to circumvent this was to introduce what is called an H-bridge. So what this allows us to do is basically reverse the polarity of the current. So at any given moment, we can pass current in one direction and then reverse the direction to create this uniformity right off the bat. Another characteristic we can play around with is our electrode design. So Amanda briefly touched on this before. What we, basically a current is going to choose the path of least resistance. But what we want is for the current to uniformly spread out throughout the material to create this Joule heating everywhere. So what we have to do is create a uniformly designed electrode throughout the perimeter of our material to ensure that heating is uniformly distributed. So what I touched on earlier was temperature regulation, and here's some data that we collected using our regulation circuit. So in the top, you can see that the user sets a comfortable temperature of 29 degrees Celsius. So we're going to ramp up the temperature until we hit that set value, and then we're just going to hover around there. So you can see that we're pretty much constant at 29 degrees Celsius, despite rapid fluctuations in the room temperature that you can see below. So even though the room temperature has been dropping quite significantly, you can see that the temperature in our material is able to hold steady. Next, we just have some thermal imaging that I was talking about. So what you can see here on the right is our unregulated thermal map, where the temperature is just going to be increasing indefinitely, unregulated amounts. Whereas on the left, you see that we have a set temperature of 28 degrees Celsius, and it's just going to hover around that value, while in this case, it's just going to keep increasing upwards of 33 degrees.
Okay, so we pretty much, Supa and Amanda talked about how we went about designing this device and the primary requirements that we set for ourselves and how we met them. I'm also going to quickly talk about the secondary requirements that we were interested in order to make this material feasible for consumer applications. And we're mainly interested in having a material that is durable and flexible. Something that's able to withstand the forces that it would experience when it is in the human body, but at the same time, as Amanda said, be able to withstand the contortions that you would have when you're running or when you're flexing your arm, and be able to withstand that. So what we did was we did our tensile tests using a tensile tester, and we compared it to pure PDMS and compared it to different loadings of the carbon filler, which was graphite powder for us. And we looked at the Young's modulus of the material, and we saw that adding the graphite powder increased the Young's modulus. But as I have here, we're able to create flexible materials that are suitable for apparel applications, even though they are able to also withstand the forces of the human body. So these are just some of the tensile tests that we ran, and we pretty much, from our preliminary material science courses, know that when we want to measure the Young's modulus, you would look at the linear portion of the stress-strain curve and take the slope of that. So beyond the tensile properties, we also wanted to make sure that this material and device was suitable for consumer applications. And whenever you have consumer applications, you always want to drive the cost down. So the goal that we set for ourselves was approximately $40 per sole of the material that we prepared. But now, considering the products and the electronics that we used, we get around to about $70 for the prototype that we have created, with about $22 being spent on the material itself, so PDMS and graphite powder, and about another $50 being spent on the electronics. So at first, this might seem a little surprising to be so expensive, but we have a plan forward on how we can go about bringing this cost down. One thing we can already notice is that we have a full-out prototyping board, which is the Arduino Mini in our design, which is not needed for a final end-user application. We can simply use the microcontroller that is in the Arduino prototyping board with a couple of analog in and out ports, which can then control the current flowing through our material. Another thing we can do is that we can explore meshed materials, for example, using carbon nanotubes to improve the efficiency of our materials, so further increasing the conductivity and thus making them less power hungry to create the same amount of heat that we would want. We would also want to go ahead and make the circuit as compact as possible, thus reducing the footprint, which is something that you would always want in consumer applications. So overall, I'm just going to quickly review through our customer requirements. We've pretty much met all our primary ones that we've set for ourselves. We have explored the tensile properties, and we have a plan forward for the bringing the cost down. Now, I'd also want to talk about our tertiary requirement, which is to have a material that's able to adjust itself to adjust the current flowing through it. One thing we know is that when materials get hot, they expand, and when they get cold, they can contract. What this means is that when you have an expanding material, the spacing between each particle will also be increasing, thus increasing the resistance. So what we can do is we can have a self-regulating material which is smart enough to kind of adjust the resistance on its own, so when it gets too warm, it can cool down by increasing the resistance, and when it gets cold, it can kind of heat up because now you're reducing the resistance when the particles come close together. So overall, I've already kind of talked about the next steps in our project. We would mainly be wanting to test out the mesh layers, develop a waterproof layers so that it's suitable for apparel applications, and of course, interface it with a mobile phone so that we can control the temperature with a Bluetooth app, and also look at how the power is how much power is being consumed, etc. At this time, I'd also like to thank Professor Vivek Maheshwari, who was our consultant, Dr. John Saad for his advice on developing the circuit, Jen Kogan and Long Pu for also advice in terms of the materials and device design. I'd also like to thank Peter Schweiger from Keysight Technologies for graciously offering us the infrared camera free of cost for us to carry out our measurements and study our material and generate those nice movies of our material heating up and cooling down. Thank you very much for listening to our presentation, and we'd be happy to answer any questions you may have. Thanks.
Thank you. Good job. All right, so questions on the floor?
Yeah. So very good presentation and the design is interesting. So my question is how big this area you want to make? I suppose you want to move someone up, right? Mm-hmm. So you have pretty big area.
Great. So for our first application, we're mainly interested in the hand and the feet, because we know that when your hand and the feet feel cold, that's when you feel the most uncomfortable. So we would be looking at a material similar in size in terms of width here for a shoe sole application, just a little longer. So in terms of material costs, we expect to be around the same or just a little higher, maybe instead of $22, $30 or $35.
And how about like battery?
So the battery we would use...
So the battery, there's pretty compact, like lithium-ion batteries that are able to source up to 2 amps, which is in the target that we're looking at. So depending on the application, for a shoe sole, you're not expecting to reach like 50 degrees, so you can maybe source an amp, and therefore you can find pretty small batteries that are able to last fairly long.
So you mentioned that you optimized the composition to about 40%. Power. Mm-hmm. Can you clarify how you went about identifying that as the optimal composition?
Of course. So we started at 100, obviously at 100% load, 100
PDMS,
of PDMS. And
so what we did was we pretty much went from 0% graphite powder upwards, and we did the IV curves. So the IV curves kind of told us, we knew from just based on back of the envelope calculations, based on the equation Amanda showed, what kind of currents we needed. So then we made a bunch of samples going from 0 all the way to 40, 50%, and did the IV curves. And the IV curves showed us that at around 40%, we were able to make samples always on the order of about 10 ohms for a substance about this size. And we went any higher, we would be kind of trading off the flexibility for the increased conductivity. At lower concentrations, one issue we ran into was, of course, the reduced conductivity, but also we ran into a lot of bubble formation when we were creating our material itself, which we tried to overcome with the desiccator, but we saw that simply by adding a little bit more of the graphite powder, we would reach a doughy consistency versus a cake batter consistency, which would drastically reduce the amount of bubbles which we had in our material. And we would always want to avoid bubbles because the air gaps pretty much act as huge resistances in your material, which is not desirable.
I have a question. We have 1 minute. So what about reproducibility? Is there any evidence of sample degradation or curve modification as you take something, heat it for an hour, bring it back down? And how could we used this over extended periods of time, have you had a chance to evaluate that?
So we haven't had a chance to evaluate that quantitatively very much, but we have noticed that obviously once you're reaching high temperatures, because of the increasing conductivity, we're seeing a lot more current travel through. So it's definitely an issue on how we're looking at the regulation, looking
What
at...
about 30, whatever, what about regular temperature usage? Could you hold it for an hour, turn it
Yeah,
on, turn
yeah,
it
for
off,
sure.
turn it off, turn it on?
Yeah,
Get the same
yeah,
outcome?
yeah. We've held steady for about 2 hours.
And you can use the sample over and over?
Right,
Yeah,
exactly.
we've tested it over
Yeah.
2 months, our current sample.
Yeah.
So I mean, this sample here, we've been testing it over and over again, and here we just show up to 1800, which is 30 minutes, but this graph just keeps on going.
So
So
if you were to run it again, same current profile, you get
yeah,
the same.
yeah. I mean, this sample we created, I think 2 months ago, and we tested it yesterday and had the same
Yeah.
profile.
Obviously, one issue is the ambient temperature, so looking at how much is dissipating versus how much we're regulating, but